What if time didn't tick the same for everyone? What if near the edge of a black hole or speeding through space, a single hour for you become years for someone else? Time isn't as constant as it seems. It's elastic, bending with speed and gravity. Welcome to the mind-bending reality of time dilation. What causes time dilation? Time dilation isn't science fiction. It's a real consequence of how the universe works. But what causes it? It all comes down to gravity and motion. As Einstein revealed through his theories of relativity, gravity and space-time, according to Einstein's general theory of relativity, massive objects like stars, planets, and black holes bend the fabric of space-time around them. This bending isn't just about the space, it affects the time itself. The stronger the gravitational field, the slower time falls for anything caught within it. Now the event horizon. Now here, in this effect, more dramatic than near a black hole, the gravitational pull is so intense that it warps space-time to an extreme. The boundary where nothing, not even light, can escape is called the event horizon. As you approach this point, time stretches infinity. To an outside observer, you would appear frozen, forever lingering on the brink of the event horizon. But to you, time would feel completely normal. Actually, from your perspective, the universe beyond the black hole speeds up. In mere seconds, you could witness a star being born, galaxies colliding, and the entire future of the universe unfolding before your eyes. To an outside observer, though, you would appear frozen at the event horizon, never quite crossing it. This is the time dilation at its most extreme.
So here you can easily calculate the time that you have close to a black hole. It's pretty simple. The T prime is the time actually you have to when you are close to the black hole. The T is the exact time that another person has far away, or like let's say on Earth. G is gravitational constant, M is the mass of black hole, R is the distance from the black hole center, and C of course is the speed of light. But what does this number mean? The G, the gravitational constant. Actually, G tells us how strong the gravitational force is between two objects with mass. It's a very small number, which means gravity is an extremely weak force compared to other fundamental forces like nuclear force or electromagnetic force. For example, the gravitational force between two 1 kilogram masses placed 1 meter apart is only 6.67 to the power of minus 11 newtons. It's very tiny. But why is it so small? Gravity is weak because G is a small number. For comparison, you can see that the electromagnetic force between two electrons is about 10 to the power of 39 times stronger than the gravitational force between them. This is why we don't notice the gravity in everyday life between two masses, unless we are dealing with very massive objects like the planets, stars, and black holes. Well, we have a very simple example here. So, suppose that we give this black hole with a mass 10 times of our Sun, and the distance from the black hole could be 30,000 kilometers. The calculation is very simple. You put the numbers and you will get the result. T multiplied by 0.13. But what does it mean? If you multiply this T to 1 hour, you will get 7.8 minutes. What does it mean? So if 1 hour passes on our Earth, only 7.8 minutes passes near the black hole. So the time runs 7.7 times slower.
One of the examples, as you know, the Interstellar movie. In the film, the crew lands on a planet orbiting a supermassive black hole named Gargantua. But time moves differently here. There actually. 1 hour on that planet equals 7 years on our Earth. So what's happening there? The planet orbits extremely close to Gargantua, where the black hole's immense gravity warps spacetime to an extreme degree. This is gravitational time dilation in action. Time slows dramatically for anyone near the black hole compared for someone far away. This isn't just Hollywood magic, it's real physics. In fact, Professor Kip Thorne calculations for Interstellar were so accurate that they were later published in scientific journals.
Time dilation isn't just a concept from movies or theories. It's happening all around us, even in technologies we use every day. For example, for GPS satellites, they are orbiting Earth at high speeds and experiencing weaker gravity compared to us on the ground. Because of this, they experience two types of time dilation. The first one, special relativity. Due to the speed, time slows down for fast-moving satellites. And second, for general relativity. Due to the gravity, weaker gravity means time speeds up. Combined, these effects cause the clocks on GPS satellites to run 38 microseconds faster per day than clocks on Earth. It may seem tiny, but if we didn't correct for this difference, GPS calculation would drift by about 10 kilometers every day, making navigation apps completely useless. Didn't know this phenomenon? Then you would ask, where am I? Why GPS is failing? And why you have 10 kilometers error per day? Neutron stars. Neutron stars are some of the densest objects in the universe. Just a few kilometers wide, but with a mass greater than the Sun. Their gravity is billions of times stronger than Earth. If you could stand on the surface of a neutron star, which you can't because you would be crushed instantly, time would slow dramatically. Every second you experience would be 30% slower compared to someone on Earth. This means that if you've spent a year near a neutron star, someone on Earth would have aged several months more than you. How gravitational waves affect time, ripples in space-time. So, when two black holes orbit each other, they lose energy by emitting gravitational waves, ripples that stretch and squeeze space-time as they travel at the speed of light. As these waves pass through space-time, they cause time dilation. Clocks in different locations would tick at slightly different speeds. If a gravitational wave passes through Earth, you would experience time behaving strangely. In one direction, where space-time is compressed, seconds would tick faster. In the perpendicular direction, where space-time is stretched, time would slow down.
Something we often take for granted is far more mysterious and flexible than it seems. From satellite orbiting Earth to the crushing gravity of the black holes, time bends, stretches, and warps in ways that defy our everyday experience. But here's the real question. If time is not constant, could we one day harness its secrets? Could time dilation be the key to traveling into the future or exploring distant galaxies? In the grand cosmic dance of space and time, we are just beginning to understand the rules, and perhaps one day we will learn how to break them. Until then, remember, time is relative, but curiosity is infinite. Stay curious, and we will see you in the next episode of SciSpice.